started. So welcome to today's colloquium, and it's my great pleasure to introduce Professor Tomonori Totani. I would call it Totani-san. Anyway, so Totani has got PhD in 1998 at University of Tokyo, working with Kachiko Sato. And right after he got PhD, he became assistant professor in NAOJ. And in 2003, he moved to Kyoto University as an associate professor. And in 2013, he came back to University of Tokyo as a full professor. So Totani has been working on very broad range of astrophysics, particularly the theoretical aspects. And he worked on high energy astrophysics, on galaxy formation, and cosmology. And even recently, he wrote a very high impact paper on the origin of the creatures. Like. Yeah, so his interest is very broad, and also he has been working on fast-reading bursts that ASIAA also actually working on these days. And yeah, so today he will tell us about his recent work on FRB. Yeah, please welcome him first.
Thank you very much. So it is my great pleasure to give a talk here. This is a very leading institute in astrophysics in Taiwan. And also I'm very happy to come here because I and Okumura-san is a long time drinking friends. So anyway, I'm very happy. So today I will talk on our recent study on the fast radio burst, and that is statistical properties and in comparison with the earthquakes and solar flares. So our work has been accepted to the monthly notice, and actually, so we are planning to make a press release from University of Tokyo about this in the maybe next week. So maybe you find some news if the press release becomes successful. Anyway, so let me start with a brief introduction for fast radio burst. It's a very short duration data tangent. The duration is typically 1 to 10, only 10 milliseconds. This was first discovered in 2006, and already 600 fast FRBs has been detected so far. But still mysterious in many aspects, and actually still very young field, and so active research are going on. And the most important feature is the large dispersion measure. Dispersion measure is often known for the pulsars, but dispersion measure for FRBs is very large. So the interpretation is that this is from coming from cosmological distances, and the large dispersion measure is because by the free electrons in the intergalactic medium. And indeed, there's already 27 host galaxies are identified for FRBs, and they are indeed at the cosmological distances of something like this. And this is indeed consistent with redshift inferred from the dispersion measure. So this gives some cosmological implications like missing variance, and it's very important researches are being made. And actually, the origins are still mysterious. But among these more than 600 FRBs, we already know that there's about 50 sources are repeating source. So one source produces many FRBs. And especially, we know a few sources of FRBs are very active. So we have a receiver and fast telescopes already detected more than 1,000 burst events from a few sources. And so we don't know the origin yet, but at least for the repeater FRBs, because of the very short time scale, and also the fact that they repeat, means most likely they are related to neutron stars. And in fact, at least one FRB has been detected from a galactic magnetar. So at least some FRBs are related to the magnetar. The magnetar is just neutron star with a strong magnetic field that is more than 100 times stronger than normal pulsars. So anyway, so today we concentrate on this repeating FRBs. And actually, as I said, thousands of bursts are detected from one single source. In this case, this is first telescope detected in this data set more than 1,600 bursts are detected from this FRB. This is actually a very famous source that is the first discovered repeat FRB. And these are thousands of events have been detected by large radio telescopes like ASIAA and crust. And so because of this large set we have, already some researchers, some groups have started to investigate the statistical properties to reveal to get a hint about the FRB sources. And one very interesting property of a statistical feature is the waiting time. So waiting time is simply the time from the previous to the next event. And if you make a plot of the histogram of the waiting times, you see the clear bimodal distribution. So this is common to all FRB sources, repeating sources. And previous studies all have mostly agreed that for this longer peak side, this is mostly consistent with a constant, most approximately constant event rate, and then the event occurs randomly, that is by Poisson process. So the data is consistent with this simple picture. But the question is this shorter peak. This peak is coming from the less than 10 milliseconds. So it is that the peak is close to the duration of each FRB burst. So most people think that this is probably related to the radiative processes or production processes of FRBs. But of course, details is not known. So this is the current situation. In this study, we compare the FRBs to the earthquakes and solar flares. So let me talk about the background for this motivation. So FRB statistical properties may be similar to earthquake or solar flares because one is first, FRBs are related to neutron star magnetars, essentially. And the magnetar flares are thought to occur by starquakes. The starquakes is neutron. We theoretically consider that the neutron star surface is a solid crust, similar to the Earth crust. And the standard picture of magnetar is the magnetic energy is diffusing out, and its magnetic energy deforms the neutron star crust, and sometimes the neutron star crust cracks, and then earthquake or starquake occurs. So that induces many flares. So from magnetars, burst in X-ray and gamma rays has been observed. So this is a standard picture of the magnetar phenomena. So it is certainly possible that FRBs may also have similar properties to earthquakes. And also for solar flares is also driven by magnetic field. Surface of the sun is a gas fluid, not solid crust, but still similarity to solar flares is first is convection energy is going into magnetic field, and the magnetic field reconnection produces the solar flares. So the magnetars are also driven by magnetic field, and the magnetic field reconnection may be responsible for the FRBs or also many neutron star phenomena. So similarity to solar flares are also very interesting. And indeed, many studies have already noted that the similarity between, for example, earthquake and solar flares. They show that if you see the energy distribution of the earthquake and solar flares, they are power of energy distribution. And they say it is so solar flares and earthquakes are similar in this sense. By the way, so we call this power energy distribution is for earthquake is called Gutenberg-Richter law. But let me make some historical account. Actually, I recently learned that there's so-called we call it Gutenberg-Richter law for the power of energy or magnitude distribution of earthquakes. But actually, I recently learned that Japanese seismologist Hyo Wadachi he found this law in 1932, more than 10 years earlier than the Gutenberg-Richter. So So I think this law should be called as Wadachi-Gutenberg-Richter law. But actually, the Wadachi's work was not so much famous because the paper was written in Japanese. But of course, the language is not a matter. So since we know now we know the Wadachi is the first for this law, so I think that we should call it Wadachi-Gutenberg-Richter. And another digression topic is actually the son of Wadachi, Hiro Wadachi, is Miki Wadachi. He was a famous statistical physicist, theoretical physicist at the Department of Physics of the University of Tokyo. And actually, I remember him because I took his lecture when I was a student in the physics department. And actually, when at the time, somehow he was called Charles Chaplin of the Department of Physics for some reason. I don't know. Anyway, so we in this work, so we investigate similarities between FRBs and spherical solar flares using the point of our work is that we use two-point correlation function so-called design in the time energy space. So this is a very popular method, mathematical method to analyze large scale structures in cosmology. And of course, Okumura-san is the expert about this method. And actually, also I think what I like to point out is this method is better than weight time distribution because weight time distribution is looking just the time between the previous to next event. But in the case of correlation function, we look all the possible pairs, and even the pairs that even in one pair, another event may exist in the pair, but still the correlation may exist. So the correlation function uses full information of a data set. So here's what is exactly we do is simply so this is a FRB data set for showing the event time and FRB energy. And so we calculate the correlation function by looking pairs. So the delta t is time difference, and there's also we calculated energy difference of the log of energy. And so the correlation function here we define that is the correlation function psi is the excess of the number of pairs compared with the no correlation or random case. So this is the no correlation case. Here no correlation case is we assume that is the first in time direction the rate is constant. And also for energy direction, of course energy distribution is not constant. But here we construct energy distribution empirically from the data set, and we assume that it is constant. So this means no correlation case is a constant rate and constant energy distribution. And the correlation function design is the excess of number of pairs compared with that case. I think as Okumura-san is an expert, this is some details of the correlation function calculations. But anyway, so we count we produce a random sample by assuming the constant rate and constant energy distribution. And simply we count the number of pairs in the data set and also random data set. And using natural estimate as a natural estimation is this is exactly by set definition of the design. But also in this field, the Randy-Sarai estimator is often used because of the better nature about the kind of size of errors. But then the error estimate has been done. Errors can be estimated by Poisson errors or more sophisticated. We estimated covariant matrix by jackknife sampling. But anyway, this kind of some details. But anyway, I will answer if you ask questions. But anyways, Okumura-san is very expert about this. And actually, I actually during this study, I occasionally asked some questions to Okumura-san, and Okumura-san helped me a lot. Anyway, so let me quickly present the most impressive result in this our study. So what we do is okay, time and energy space. We calculate correlation function. And here, this is we calculate a two-dimensional correlation function, delta t and delta log e. But here, this is I'm showing a one-dimensional time so integrated over energy. So we calculate the time correlation function as a one-dimensional. Anyway, so what we do is okay. So from this data set, we calculated the time correlation function design. And the question is actually, why is FRB and why is earthquake? So can you tell me which is which? So Kumar-san, so which is FRB? Are you sleeping? So can you tell which is FRB? Which is earthquake?
This one earthquake.
This is earthquake. You lose. This is FRB, this is earthquake. But as when we got this result first, I'm very surprised because of similarity. I mean, the correlation function is this correlation function is power law plus flattening region in short time intervals. And actually, also the flattening time scale is about millisecond for FRBs. And then as in the case of the earthquake, it is about 1 minute. But I think it is similar to between the similarity between the two because this time scale is close to the typical event duration. So FRB event duration is about millisecond, and in the case of earthquake, the duration of one event is typically 1 minute. So if you see the delta t close to the duration of one event, there is some flattening. But otherwise, it is a power law. So it looks like very similar. So let me present the more details over our study. So we use 3 famous and active FRBs, repeater FRB sources. Typically, leadership is something like this, and there are some host galaxy properties. But anyway, so we use 3 different FRB sources. And also we took many data sets. I mean, also, even from one source, there is in the literature, there are different data sets. For example, we use both RSIMO and fast observed result, and based on the literature. And so in total, we use this 7 data set. The total amount of the burst is close to about 7,000. So this is one example of our calculation. So this is time and energy scatter plot. And this is bimodal. This is the weight time distribution. That is a bimodal, of course, found in previous studies. And this is a distribution of number of pairs in the delta t and delta log e space. And if you compare this the pair count distribution to the case of that of the random sample, you get this correlation function. So this here, the correlation two-dimensional correlation function is plotted as a color. This you see here is almost no. In this region there is no signal at all. But here, correlation function is close more than 1,000. So very strong detection. And here again, this is a time integrated over energy. This is a one-dimensional time correlation function as a function of delta t. And again, so this is here. Do you have another pointer? So.
Is it okay or should I bring the
Okay, so here you see the correlation function for 7 different data sets. But all 7 different data sets, including different sources, this region is a power law. Here is this is the no signal. That's because it's too weak signal. So consistent with noise. Here some flattening. So if you go to the millisecond scale, there is some flattening. And there is some difference between some data set come down, some data set is constant. So this is most likely, this is a bit complicated, but this is, we consider most likely some artificial effect because in this, if you look at on the millisecond scale, sometimes 2 bars peak observed, but so when, so in this case, overlapping multiple events are classified one event. So if you one burst occurs and the next burst occurs maybe 5 milliseconds later, in that case, the lifetime is connected. And in that case, these are treated one event in some catalog. And it's kind of this kind of a subburst problem. So the treatment of subburst is not there's no standard method in the community. So in these different catalogs, treatment of subburst is different for the different papers. So probably this explains this different behavior here. Okay, anyway, so these curves can be roughly fit by this delta t plus tau, some flattening time scale constant tau with a power. And this is a fit by this functional form to each data set. And as I said, here is you can see the effect of the subburst treatment here, because this catalog, in this catalog they gave this catalog with subburst as well. I mean, they classify if they find multiple peak bursts, they consider as one single event. But still, also in the catalog they give information on each subburst within the single event. And here, this curve is we treated all subbursts as an independent event. We get this profile. But this cross is if we combine the kind of subburst into a single burst, then in that case, suddenly the number of short delta t events disappear. So depending on the treatment of subburst, so this behavior becomes different. So we should be careful. Anyway, so the region less than 10 milliseconds is a bit difficult to treat because of the subburst problem. But anyway, overall, the data can be fit by power law plus flattening at about less than 10 milliseconds. And okay, so furthermore, also I should comment on that this functional form is close to the Omori-Utsu law of aftershocks in the field of earthquake. But okay, I will talk about. I will come back to it later. But still, another important point is okay. So here, upper panel is just showing the correlation function, but lower panel, I'm showing the aftershock rate. That is, I multiply to the mean burst event rate to this. In this case, so in this plot, where correlation is 0, this was just 1. But in this plot, this level shows the mean event rate. Here, in this region is the excess compared to the mean event rate. So as a definition of the design, so this part means correlated aftershock rate. That is the rate of aftershocks following one event. And what is interesting here is, okay, so if in this plot, aftershocks, mean event rate have a very large scatter, depending on of course, if you see different FRB source or different, the mean rate is different. And even within one single source, activity changes. So sometimes event rate is high, sometimes event rate is low. But interestingly, so the aftershock rate of the correlated part, aftershock rate, is relatively constant against this large dispersion in the mean rate. So this is very interesting properties. And here this is a rate, aftershock rate is delta t inverse. If the rate aftershock rate is less than this means if you make an integration of this part, is less than 1. And indeed, so the integration of this gives a number of expected number of aftershocks. Here I define n. And indeed, this is this lower than this curve, this line. So typically we found n is about 0.1 to 0.5. So this means typically 10%. This is the probability of 10% or 50% for the aftershock occurrence. I mean, if one FRB occurs, then there is a 10% to 50% chance of observing correlated aftershocks. Well, this, in other words, multiple aftershocks to one event are rare. And as I said, this aftershock rate is almost also universal. Even if we observe the different sources, different neutron stars, but still, the aftershock rate is relatively in this narrow range. So this suggests these properties are universal. Okay, so now let's see anyway. So this form of aftershock rate is actually famous in the earthquake field. It's a so-called Omori-Utsu law. This is first thing proposed by Fusakichi Omori in 1894. He suggested the rate of aftershocks after following one big earthquake can be described by this form. And this is extended to general power law by Tomonori Totani in 1957. So anyway, this is quite well established law in the earthquake. So it is. So then we adopted our analysis method to the earthquake data. So we took from a Japanese earthquake data, and I took some different regions. For Narita, Shoshi, and there's a greater Kanto region, and also some Izumo region to see the difference of location and also difference of region size. By the way, so when I was looking earthquake data, one day I made this plot. I was curious about this here. This I just plotting time, event, earthquake time, and earthquake energy. And here's some sudden change, very sudden change. I was very curious what is happening here. Maybe some artificial effect, maybe some detection efficiency change or something. But actually, after some time, I realized that this is the 2011, March 11. So this is the data from Kanto, Tokyo region. But this is famous great, huge Tohoku earthquake. Actually, the people who live in Tokyo all know that after this event, we experienced many small earthquakes. So this certainly should be just appearing on the data. By the way, I remember a news that when this tragic event, I think Japan received extraordinary amount of donation and help from Taiwan. So we should appreciate that.
Sorry, but this x-axis is a time from the first event.
The first event means this. I picked up some data cut from the catalog. So that's simply the first event that I cut from the data. So no meaning. Anyway, so I use this 5 data set. The events are typically including about 1,000 events for each data set, similar to FRBs. And here's an example of the design calculation. And it's so weight distribution is not so clear in the earthquake. So possibly you can see some excess around here. So these appears as a correlation function signal around here. So for the earthquake, it is not surprising that we find the Omori-Utsu law for the aftershocks. So the correlation function takes the same form, the power law plus flattening. And then the flattening, as I said, flattening time scale is about 1 minute. That is the typical duration of the event, earthquake.
So for earthquake case, how do you construct the random control?
Oh, that's the same as completely same as the FRBs, assuming constant event rate. And also for the energy direction, I assume constant energy distribution. And energy distribution is simply empirically constructed directly from the observed data. So basically, in our code, only input is a time and energy data set. And also, assuming the constant event rate and constant energy distribution. Energy distribution is also constructed from the data set. Yeah.
So you also take into account the fact that you have more earthquake after this March 11. You construct the random curve also the time direction also from the data.
Data, yeah, exactly data. So I took many data sets, so including before and after the total earthquake or in different regions. For each data set, I constructed the energy distribution and assuming constant event rate. Now, so you can see as a function of the time correlation delta t, the time correlation function, you can see the similarities. Okay, so in this region, the power law appears, and there's some flattening in the shortest time interval, so it looks like very similar. And even more similar, surprising is the stability of the aftershock rate. And if you convert into the aftershock rate by multiplying with mean rate, so even if the mean rate changes in the case of earthquake by a difference of size, region size, or difference, or also before and after the total earthquake, the mean rate changes. But even if mean event rate changes, the correlated aftershock rate is very small. So it is very, very stable. And furthermore, this is a critical line about n equal 1, but here, earthquake and FRBs both are about very similar order, but one order more is smaller. So this means the integration of this part, that means the number of correlated aftershock is about 0.1 to 0.5 in both cases. So this means not only the shape, but the absolute normalization of this correlated aftershock rate is very similar between the two. And for effort, so and this is for the weight. This is for the weighted distribution. So this is two-dimensional correlation function xi. Another similarity I can point out is so we see that strong time correlation in the short delta t. But here, if you see the energy direction, this along the energy direction is almost constant. This indicates there is no or only weak correlation between in the direction of energy. So this means even if one aftershock occurs following one event, the energy is not much correlated. This is another point of similarity. So let me summarize about similarities. I can list up 5 similarities between FRBs and earthquakes. First, aftershock rate follows this Omori-Utsu law, and the expected number of aftershocks to each event is about 0.1 to 0.5. So this can be explained by universal picture that each event produces about 0.1 to 0.5 aftershocks as the expectation number or probability. And here there is no discrimination between main shock or aftershock. So every single event produces some aftershocks, which is according to this universal law. And actually, this is actually not new to the earthquake field, because this picture is known to describe the earthquake data well. It's a so-called ETAS model. Maybe it's a correlation function calculation may be new for the earthquake data, but the picture is already consistent with what is known in earthquake studies. And also, the third point is this flattening time scale tau is close to the event duration. That is about msec for FRBs and 1 minute for earthquakes. And also the aftershock rate, correlated aftershock rate is constant or stable against the change of the mean event rate. And finally, there is almost no correlation between time and energy. So I think these are very, I suppose, striking similarities. I mean, I cannot believe that this could happen by just a chance or accidentally. But the only difference is the power law index. As you see, the power law is something of earthquake is more flatter. So it's according in terms of Omori-Utsu index P, in the power index, FRB is about 2, but earthquake is about 1. This is only difference. But actually, if we check the earthquake literatures, the P of earthquake depends on the regions. I invested only Japanese earthquake data, but maybe in the different region, maybe sometimes they found different P. So in some earthquake data set, the value of P close to 2 is also reported. So maybe this is also marginally consistent within the range reported by earthquakes. Okay, so now we find that the earthquake and the FRBs are very similar. So how about solar flares? So we took the data from Hinode solar flare catalog and we constructed 2 samples. It's a high state, solar cycle changes by a period of 11 years. So we took high state and low state data with high and low mean event rate. And here is some examples. So this is time and time. So here, in the case of solar flare, we took X-ray solar flux, X-ray solar flare flux as a proxy of the energy. And we calculated this is the wake time distribution, wake time distribution. And anyway, so this is two-dimensional. This is a two-dimensional correlation function. But anyway, so we found that the solar flares are very different. You can see, so this is a one-dimensional time correlation for the solar flares. We don't see any power law, but also correlated correlation signal is observed beyond the critical line of the aftershock rate is the same as the aftershock rate of the delta T inverse. This indicates that if you integrate this part, number is more than 1. This indicates sometimes one solar flare produces multiple shocks. In the case of earthquake of FRBs, one event produces at most one event of aftershock. And another striking difference is two-dimensional function of energy correlation. In FRBs and earthquakes, the correlation function is almost constant along the energy. But in the case of solar flares, you see the strong peak of the correlation function also for the energy direction. So it's peaking at delta 0 about the difference of the load of energy. So this means when the solar flare occurs correlated to the previous event, then their energy is very similar. And it is these features is all found you can see. So if you see the time and flux plot of solar flares, you can see many spikes clustering of solar flares. This indicates multiple generation of solar flares. And also you can see the strong clustering in the energy direction also. So these are actually very different from the FRB and the earthquakes. So these solar flares are different. One is no power law profile, and aftershock rate is larger than delta T inverse, so multiple aftershocks is produced, and a strong correlation in the energy direction. So let me summarize and conclude. So FRBs are remarkably similar to the earthquakes and in time energy correlation with the universal laws on the aftershock statistics. So I can list up 5 similarities. So each event induces typically 0.1 to 0.5 aftershocks as the expectation number or probability. And the aftershock rate obeys the Omori-Utsu law of earthquake with this formula. And the flattening timescale tau is close to the event duration. The msec for FRBs and 1 minute for earthquakes. And even if the source activity changes, so mean event rate changes, but correlated aftershock rate remains very stable. And finally, almost no correlation between time and energy. But these, compared with this, solar flares are very different from FRBs or earthquakes. So, what are the interpretations? So we think the most natural interpretation is certainly because of the similarity between FRBs and earthquakes. So this suggests repeating FRBs are produced when energy stored in the solid neutron star crust is liberated by cracking of the or seismic activity. But what is the origin of difference from the solar flares? Well, this is probably coming from the surface and nature of surface. Because Earth and neutron star that at least for Earth is of course surface is solid. And also theoretically we believe that the neutron star has a solid crust on the neutron star surface. And so sometimes cracking starquakes would occur. That has been theoretically considered for many years. On the other hand, in the case of sun, even though it is energy source is maybe the same magnetic field that is same as the magnetic Earth, but the surface of sun is not solid, but gas or fluid. So maybe that's maybe difference is coming from this fact. But the only difference between FRBs and earthquakes is the value of the Omori-Utsu index P. And P for FRB is about 2. It's larger than the earthquake. But still, I think this is very interesting because in the earthquake studies, P, the Omori-Utsu index P, it depends on. They think that it depends on the properties of the Earth's crust. So in the future, I think this one interesting possibility is okay. So studying FRBs and using some theoretical modeling of this Omori-Utsu index, maybe we get some information about the solid neutron star crust. Of course, that means we get some information about the very high dense nuclear matter. But I think this is a very interesting possibility. And finally, also I present some discussion. So one interesting fact about the FRB repeaters is they show the change of activity with some period, the periodic activity change. The most famous one is for this FRB, the FRB rate, event rate changes with a cycle of 16 days. 160-day periodicity also suggested for this first discovered repeaters. And I think the origin of this periodicity is also a very interesting question. So one speculation from our result is okay. So this activity may be explained if the seismic activity on the neutron star surface can be if the periodicity changes. If seismic activity of neutron star surface periodically change, then we may explain this. And if the happen, for example, if a neutron star is forming a binary system, and if it's eccentric binary, then the neutron star will experience pericenter periodically. And when the companion star becomes closest to neutron star, then tidal force becomes the maximum. Then that tidal force would induce some change of the neutron star crust, and that will induce the seismic activity. This kind of process may explain the periodicity of the repeater FRB sources. Another impression, discussion is for there is one repeater FRB found in a globular cluster in M81. As you know, globular cluster is a very old system. You only have very old stars. So it may be strange that we have some active stars in globular clusters. But in the globular clusters, there are so many stars in high number density. Sometimes the neutron star in a globular cluster may encounter with another star in the globular cluster. In that case, they experience strong tidal force, tidal interaction. If this induces some seismic activity of neutron surface, maybe this explains the repeater FRBs in the globular cluster. So these are some speculation, but I think this is interesting speculation. So okay, so that's it. The last here. So thank you very much.
Thank you very much. Questions? Yeah, please.
So the waiting time scale, there's a bimodal distribution. So one is like I missed that part. So there is two peaks. So first peak is related to first shock, and second peak is related to aftershock, right? Or
okay, this is what. So
in the beginning, yes, this one.
yes. Okay, so. Okay, so then your question is the first peak and the second peak. What is your question?
Yes. So what are the mechanism behind these two peaks? Right?
Okay. So, yeah. First, for this peak can be first forget here. Even if you assume some just constant event rate and produce random event, you will expect this peak because this is right time distribution. So this peak is simply the mean event separation. So that's calculated expected by mean event rate. But here, we know the correlation. So in the case of random data, we don't expect this. But because of the correlation, so aftershock occurs. So after one event, there is a aftershock occurs with a higher probability by correlation. Then we see this peak.
So my question, I saw both in earthquakes and FRBs that the shorter wait time data points are uncertain. Can you comment on why that is? Is this just observations or is if you look at any generic, there's a lot of uncertainty in the.
Oh yeah. Okay.
Shorter region. Yeah.
Okay. This is simply coming from the statistics. I mean. Well, this is a case of earthquake, but simply the correlation function is calculated by the number of pairs. We look at pairs, but if you look at very short time interval, the number of pairs is very very rare. So this is a statistical error becomes large. Statistically.
And the other question I have is a little naive because I'm not an expert in either earthquakes or neutron stars, but I was wondering, earthquakes are a generic consequence of changing tectonic plates, so there's some form of, I would say, wave propagation within the solid or not so solid surface, more porous surface that lets the waves transfer and become bigger and then comes to the surface. There's a lot of massive earthquakes in the surface, but in terms of neutron stars, the density is so high. I'm wondering how the wave even propagate because. It would just not allow. It's so, in some sense, it's so dense that it feels like it should not allow any propagation.
Okay, I think first in the case of Earth, maybe I'm not so sure what you're doing in the wave propagation. I mean, wave propagation of an earthquake wave is after one earthquake occurs by cracking of the surface. So the wave propagation is maybe so we feel earthquake by the wave propagation. Yeah. So I'm not so sure what happened. I'm not so sure about the FRB about wave propagation of FRB may not be not correct, maybe different from FRBs. But my point is, I think this is we are looking for the just event of just cracking or just kind of starting point of earthquake. So if it is similar, so simply this is coming from the solid nature of the earthquake. In the case of earthquake, the earth crust is solid. And so wave propagation is rather maybe unique to earthquake, but it is also we don't know how FRBs are produced after cracking of the neutron surface. So this is another issue. So this is a kind of an issue of the emission mechanism of FRBs. So in this area, this is an interesting topic, but here I don't say nothing about it. Simply, my proposal is FRBs and earthquake are produced when the solid surface is cracked.
Well,
So the conclusions you reach here are based on data from repeating FRBs. Do you think any conclusion you have here can be applied to non-repeating FRBs?
That's a good question, but yeah, it's difficult because for the non-repeating FRBs, there are many theoretical proposals, and we have actually the information is completely so information for the non-repeating FRBs is very limited. So especially actually, at least personally, actually I propose that the non-repeating FRBs are coming from binary neutron submergers. So in that case, it is completely different. So it is possible that non-repeating FRBs are completely different population to the repeating FRBs. That is one possibility. On the other hand, another possibility is non-repeating FRBs actually really, in fact, they may be same population, but simply they occur only once within our observing time. In that case, if we observe so long time for the non-repeater FRBs, maybe we will find repeating events from such a source. And if we apply this same analysis, then we may get a similar result. That is another possibility. But currently, I cannot say more than that.
Since they are non-repeating, does that imply they don't even have aftershock? So there cannot be crack.
Yeah. I think that is one way possibility. I suggest what I show is after one event, after one event, relatively on a short time scale, they produce aftershocks. So one possibility. I think your point is very nice. So being only one detection of only one event may disfavor the may indicate is no aftershock at all. I need to maybe do some statistical analysis to examine that. But yes, maybe you can use this fact to say that okay, so non-repeating FRBs are different from the repeaters. I think that may be an interesting research topic. But yes, but I need to investigate more carefully.
sorry, could you explain the meaning of the correlation below the time duration?
Correlation, simply but I think the time duration simply for this data set we use one single event time for one event. In this case, probably there is each time probably some uncertainty comparable to the each event duration.
Right, and then why do you have a correlation below that uncertainty?
I think
you have this flat behavior.
Yeah, flat behavior.
Why it doesn't go to zero, but it has to stay as a constant?
Stay constant. So I think okay. One reason is the reason becomes flat is when this means that the delta t is comparable to the duration. So in that case, then sometimes some bursts are connected to one single event. The observation is treated as a single event. Another possibility, also in the case of earthquake, and in the earthquake also the origin of the flattened time scale is actually a difficult issue, not too much understood. One difficulty is selection effect. I mean, after one earthquake, of course, then still they are oscillating. And then if the second aftershock occurs, but still if previous earthquake is happening, continues, then it is difficult to detect the second one because of mixture. So in that case, even if the power law aftershock true rate goes up, but because of the selection effect, or even if delta t is close to the event duration, they are mixed, and so the detection is very difficult. So anyway, so that could result in the change of this power law.
Yeah, I understand the correlation function decay below that scale, but I'm curious why it doesn't go to zero but it stays at constant.
But that is the problem, because in some cases they detect if the you can detect very large, event duration depends on the each event. Sometimes the event duration is short. Sometimes event duration is short. So if you find two events with each of the duration, you find those short duration event, and right after that another you find short duration event. The delta t can be small. So that comes in the data set.
Okay. Yes. And do you have such a finite duration for the solar flare?
Yes, solar flare is also some duration effect. So typically solar duration, for solar flares, the typical duration is about maybe 30 minutes or 1 hour level. So this is also, okay, I mean in this region, if you observe this region, I think duration effect comes in. So indeed, the data comes down. So it's consistently. So this drop is probably due to the duration effect.
I thought if you have any event which has the autocorrelation, okay, then and if there's no typical scale, then you expect to have a power law, and also it's expected you have this duration, the event has a finite duration, then it also make it flat. So yeah, I think it's expected to have a similar similar behavior between FRB and earthquake, or even the other event.
Yeah, I think if this power trend, it's for example, if my speculation is probably this similar profile is coming from the cracking of the solid matter. Then if then if other events induced by the cracking of the solid matter may produce similar profile. Basically this power law and that continues to the power law continues to the short duration of delta t comparable to the duration. I think that is possible.
Any other questions?
I'm not familiar with this field, but so why don't you think that this kind of analysis can be done event which are more related to the neutron star activity? For example, event regarded as a glitch or something.
Okay, yes, yeah, that's a good question. Okay, so because I was interested in FRBs, so first I applied to this method to FRBs. But yes, I see some glitches are also. So magnetars are also producing many X-ray bursts or something, and so maybe glitches are maybe event number is too small, so probably difficult. But actually we have a data set about, for example, for magnetars, there are many data sets, hundreds of the bursts in the X-rays or gamma rays, and it is interesting to see up to adapt this same analysis to this data set. We are now thinking about that.
Any others? Okay, so Yatsukai-san will be here only today. So if you want to talk to him, please talk to him before he leaves. Okay, yeah, let's thank Yatsukai-san for the great talk. Thank you.